Welcome to 7.2 Systems of Linear Equations in Two Variables. So we're primarily just kind of talking about linear equations, and you're welcome to look at method of eliminations, but by the time you're taking this course, this is review for us. So for elimination, what we're looking for here, we've got two equations, a nice convenient standard form here where the x's are grouped over the x's, the y's over the y's, and our constants are isolated. When we have equations of that form, we could go ahead and very conveniently solve this equation for x and get 12 minus 7y. Take quantity 12 minus 7y, substitute it in for x, solve this equation on y like we were doing just a substitution problem. But elimination pretty nice. And again, I know this is review, so I'm not going to spend too much time getting us up and running. The lead coefficient 1 and 3, the least common multiple of 1 and 3 is 3. I would say the x's can match up at 3. Whereas the y's, 7 and 5, could conveniently match up at 35. I'm going to make the x's match up at 3. And the first equation is already, the second equation already has a 3. The first equation, I want to make this a 3, but in all honesty, I'd rather it be a negative 3. I'm going to multiply the first equation by negative 3. And I get negative 3x. I get minus times plus minus 21y equals minus 3 times, or negative 3 times 12, negative 36. And when I add these equations together, equal things plus equal things result in equal things. I can do that. I get x's cancel. I get negative 26y equals negative 26, or y equals 1, meaning my solution is something 1. And now y may be replaced by 1. I can go any equation I want, replace y by 1. I think I'm going to use the first equation. I get x plus 7 times 1 equals 12, or x equals, subtract 7, 5. So the intersection of these two lines is at 5, 1. Okay, number 20. The u's least common multiple 6, not too bad. The v's least common multiple 55. I'm going to have the u's match up at 6. I'm going to multiply the first equation by 2 to get 6u plus 22v is 8. And the second equation, I'd like to get a 6 here, but not really a 6. I'd rather get a negative 6. I can multiply this equation by positive 3. Negative 6u minus 15v equals 3 times 9, 27. It's common to see people forget what I refer to as the follow-through. Multiply the 2 by the 4, multiply the 3 by the 9. We combine these. The u's cancel. 22 minus 15, I get 7v equals 8 and 27, 35. V is, divide 7, 5. U before v, v is 5. I can put 5 in anywhere I want for v. I think I'm going to put it in the first equation. 3u plus 11 times 5 is 4. 3u plus 55 is 4. Subtract 55. 3u is negative 51. Divide 3u is negative 17. And we've got it. Okay, nice thing about these equations, we don't have to work with fractions if we don't want to. I notice in this first one, I can multiply everything by 2, and that'll take care of my fraction issue, and I would get an x minus a 4y equals negative 5. And now I note that my x's are already a perfect match. Negative 1, positive 1. In fact, if we're looking beyond that, the y's are a perfect match. So I combine these, I get 0, I get 0, and I get 0. And so here's where I'd ask the class, when does 0 equal 0? Always. And there's a temptation to say all real numbers here, but it's not all real. It's not all the points out in the plane. What this means is these two lines are the same line. They're overlapping. We could take a look at and graph them and see that, but they're overlapping. So it's true there are infinitely many solutions, but it's not all real numbers, isn't the proper answer. There's just an infinite number of points. We could also say it's all points on the line. For instance, here's a line, there's a line. On the line, negative x plus 4y equals 5, because they're really the same line. And you could have used this here, or you could have used this variation. They're all the same line. Okay, again, we don't have to work with fractions. I would multiply this first expression by 2, oh, actually by 6, because I need to cancel a 2 and I need to cancel a 3. So 6 times, when I distribute 6 times this first term, 6 divided by 2 is 3, times the 2x plus 5, plus 6 divided by 3 is 2, times the y minus 1 equals, careful, 6 times negative 1, negative 6. Let's clean that up. Distribute. 6x plus 15 plus 2y plus times minus minus 2 times 1, 2. I get 6x plus 2y equals negative 6. Let's see, I'd have a plus 13 here, so I get a minus 13 over there. Right? I'd get a plus 13, so minus 13. So 6x plus 2y equals negative 19. Now, I look at this equation and this equation. The x's could match up at 6. The y's could match up at 2. I'm going to multiply this equation by 2. And I get, could we just come back, please? Thank you. And, excuse me for that. And I get 2 times 2x, 4x, minus 2y equals 24. Or I get 10x equals 5. X is 1/2. So my ordered pair solution is 1/2 something. And now I can put 1/2 in anywhere I want for x. I'm putting it in right there. 2 times 1/2 minus y equals 12, or 1 minus y equals 12, or add y to both sides, subtract 12 from both sides. Y is negative 11. Okay, so when we have, one thing we've noticed in the last two problems, when we have equations and we have fractions, we don't really have to work with them. We don't have to work with decimals either. I notice if I multiply this by 10, the decimal would move one place. And let's just rearrange this. I'm going to jump around a little bit here. This would be 63x plus 72y equals 54. And now I notice that I can multiply by 1/9 and reduce this. 7x plus 8y is 6. Let's take a look at the second equation. We could multiply this one by 10. But because all of the decimal places are even, we can actually get out of this multiplying by 5. Let's see, that would be 25, and 5 times 0.63. 25 and 3, that's 28x, plus 6 times 5, 30. 5 times 0.42, 32y, equals 5 times 4, 20. 5 times 0.84, 24. And what I notice here is all of these could reduce by 4. So if so here's one of my equations. I'm going to multiply this one by 1/4, and I get 7x plus 8y equals 6. How about that? I have the same line. So I could stack these and subtract them, but both of these I'm claiming now are the same line. So we have infinitely many solutions, or all points on 7x plus 8y equals 6. All points on that line. Okay, little tricky here. My first thought here might be to multiply both sides by x times y, the least common denominator, but I'm going to get a nasty xy term that I'm not going to know what to do with. I'm going to think of this like this. 2 of these 1 on x's minus 1 of these 1 on y's. And here I've got 6 of these 1 on x's plus 1 of these 1 on y's. this was equal to 5, this was equal to 11. And the 6 and 2 could match up at 6, but the negative 1 and the positive 1 are a perfect match. If they weren't, I might multiply the first equation by negative 3 and stack it underneath here to get my 6 times 1 on x's to cancel. But this is a perfect match. I'm going to add them. I get 8 of these 1 on x's. This is 0 equals 16. If I multiply both sides by x, I get 8 equals 16x, or x is 1/2 when I divide by 16. And I can put that in for x anywhere I want. I'm going to put it in the first equation. I'll put it in the second equation. I get 6 on 1/2. Zoom out of here a little bit. I get 6 over 1/2 from right here, plus 1 on y equals 11. That's 6 divided by 1/2. 6 divided by 1/2 is 6 times 2. I get 12 plus 1 on y equals 1. Or I get 1 on y equals negative 11. Is that all good? Did I get this right? This was an 11 to begin with, wasn't it? This was an 11, sorry. It's an 11. So this is 11. I subtract 12 and I get negative 1. Multiply both sides by y, I get 1 equals negative y, or y equals negative 1. Okay? Then, find the point of equilibrium of the demand. So we got a demand equation and a supply equation, some business application here, but the math pretty easy. The point of equilibrium is the price P and the number of units X that satisfy both the demand and the supply equations. But this is equation of a line. This is an equation of a line. The slopes aren't the same. This has a slope of negative 0.05. This has a slope of 0.1. These lines intersect somewhere, and that's all they're asking for. But this is already solved for P, and this is already solved for P. 0.05 slope, 0.1 slope. And so if P equals this, and I want the same value P to equal that, it's just this equals that. So 100 minus 0.05x is supposed to equal 25 plus 0.1x. I think I'll subtract 25 on both sides. Add 0.05 to both sides. So x is 75 on 0.15. X is, you can go to calculator on this if you need to, but we can get out of that. X is 500. And if x is 500, we can find P. P equals either there or there. I'm going to use this one. P is 25 plus 0.1 times 500, or 25 plus 50, P is 75. And if you want to check it, put that 500 back into here and see that we get the same thing. All right, motorboat traveling with a current. Rate times time equals distance. Rate times time equals distance. Takes 40 minutes. Now, usually we talk about rates in miles per hour, not miles per minute. So we're going to do some conversion for that downstream. And then we come back and we travel back upstream, and it takes longer, but the distance is still 20. So I'm going to have a downstream part of the chart and an upstream, sorry, that's terrible, W, and an upstream part of the chart. So my time going downstream is 20, my time going upstream, or excuse me, is 40, my time going upstream is 60, the distance is 20 both ways, but my rates are going to change. If the current was 10 miles per hour and my boat was traveling 15 miles per hour, or was registering 15 miles per hour, it would actually be going 25. It's just, you know, if the boat wasn't wasn't traveling at any speed by itself in a 10-mile-an-hour stream, it would be traveling 10 miles an hour. It would just be floating with it. Now, the problem with this is these times I would rather those be in hours, so I'm going to reproduce this. Here's my down, here's my up. The rate is 40 on 60th of an hour, or 2/3, and the rate is just, or excuse me, the time is 60 on 60, just 1 hour. Equals 20, equals 20. So my downstream is going to be faster, so I'm going to call it the boat plus the current. And upstream, the boat's fighting against the current, so it's the boat speed, but minus the current is our actual rate. So now, this first equation, I'm going to go ahead and go B plus C equals 20. I'm going to cross multiply the 3 on, or I'm going to multiply by 3 on 2 to cancel 2/3. And my second equation is just B minus C times 1 equals 20. So let's see, this is B plus C equals 20 divided by 2, 10 times 3, 30. I want to solve these equations, but how convenient. So B equals, let's see, B equals, is that right? This is 2B when I add these, I'm sorry. B plus B, 2B, the C's cancel, equals 50. B is 25. If I put 25 in, I'll put it in here. 25 minus C equals 20. Add C, subtract 20. C is 5. So the boat is 25 miles per hour, and the current is traveling at 5 miles per hour. Not too bad. Maybe the trickiest part of it is just, I mean, yes, we could have answered it in minutes per hour, but that's just not the norm. You know, we don't, it doesn't give us too big. So if I heard somebody's traveling at 4 minutes per, or 4 miles per minute, the first thing I'm going to do is go to some kind of conversion on that. They'd be traveling pretty fast, by the way. Okay, so there's our assignment on this. This should be pretty much reviewed, but there's going to be some word problems in there we'll probably end up talking about, but should be able to hammer this out pretty quickly. As always, let me know if I can help.